Welcome to In 5 Minutes. The agenda of this clip is to implement a 2-input XOR gate in different styles ranging from static to Cmos, including Pseudo Nmos and dynamic. Okay, let's get started. If you see on the screen, I have written the expression for the XOR gate y equal to a b bar plus a bar b. In the previous clips, I have taught you the shortcut of how to implement the static circuit or the schematic from the expression. And the trick was hide the bar. That was the first step. But here in the expression, I don't see an overall bar present at the top of AB bar or A bar B. And hence, I would want to find that bar so that I can use my shortcut trick. So for that, I'm going to do this. See if it makes sense to you. AB bar plus A bar B. And I'm going to put double bar. Double bar means A double bar is equal to A only. So this is exactly the same thing which I have written. There's no change at all. What we are going to do is, we are going to take this part, the upper bar, we will keep it for our implementation which we want to hide. So the lower bar and the term underneath it, we will try to simplify using De Morgan's theorem. Let's first quickly write what is De Morgan's theorem. It says that A plus B the whole bar is nothing but A bar dot B bar, and AB the whole bar is nothing but A bar plus B bar. So this is what I have written in De Morgan's theorem. Now quickly let's try to simplify the above expression using De Morgan's. It's nothing but the following bar. This is the first bar which I had. The internal bar I am going to simplify using De Morgan's. So that is nothing but A bar dot B, that's correct, into whole bar plus get substituted with the dot into A dot B bar into whole bar, which is nothing but equal to A double bar plus again De Morgan's plus B bar. This is very straightforward. We have already studied this in the lower classes. Dot A bar plus B double bar. The final thing is nothing but A plus B bar dot A bar plus B. So I've got an expression underneath the bar which is nothing but A plus B bar into A bar plus B. So let's hide this bar, and whatever is below the bar, let's write it, and that is nothing but my pull down network. This is underneath the bar. So this is the first term, this is the second term. Let's implement this. The first term is A plus B bar. Plus means parallel and pull down. So NMOS, A transistor with an input A, plus means parallel, B bar. This entire first term is dot. Dot means series. In series with A bar plus B. A bar plus B is nothing but plus, so parallel. This is in series, so this is the series connection. A bar, again an NMOS, plus means parallel, B, and this is going to be my ground, and this is a series connection. So I got my pull down circuit. The exact opposite to my pull down circuit is going to be my pull up circuit, exact complement. So let's draw that. Here A is parallel to B bar, so here A and B bar will be in series. It's a PMOS now. A in series with B bar. This entire thing was in series, so now it's in parallel. And here A bar was in parallel to B, so here it will be again series. A bar, B, and this completes the exact complement to my pull down network, and this will be connected to my output because the output is taken from the between part of pull up and pull down network, or PMOSes and NMOSes. So this is what I exactly get here. And if you put the different values from the truth table of A and B, you will see that your logic or your functionality is achieved.